All right, good afternoon. Let's get it going so I can take an extra minute to talk longer. Thanks for coming to our session. This is one of the last sessions. And thank you guys for a great presentation and a great setup for my talk, actually, because I'm also using NAPE imagery in this talk. And the purpose of today's talk is actually to look at the new quality level 1 LiDAR data that was put out by the state, NOAA and USGS. We leverage both. Along with NAPE multispectral imagery to actually test how well these two data sets would perform for wetland mapping and classification. And I definitely want to give a huge shout out to my former grad student, Patrick Connell, who is now a research specialist at UNCW, who did a lot of this work for his master's thesis. So, why wetlands? Well, we live in North Carolina and over in New Hanover County, where UNCW is at. And for the majority of the coastal plain, we are talking about 76% of our original land cover was wetlands, right? So therefore, wetlands are important. They provide incredible functions and ecosystem services to us as humans. They also provide habitat. They help with our water quality, and especially in the coastal region, we're very concerned about the presence of wetlands and their health because of flood mitigation services they provide. But they're also incredibly threatened. So in the last 50 to 100 years, we've lost more than 50% in the Atlantic coastal plain, even more so than that. And as my colleagues here said earlier, in New Hanover County, Brunswick County, Pender County, we are seeing incredible population growth, and all of that translates in what we end up converting from to suburban is typically some sort of a wetland. So there's huge interest in wetlands, in mapping them, and you'll see in a second why. So for mapping wetlands in the state of North Carolina, there are two agencies that are mostly in charge, right? The U.S. Army Corps of Engineers, they only delineate. They essentially they delineate wetlands for regulatory purposes. The data is not publicly available, but the data that we do have publicly available is from the Fish and Wildlife Service, also known as the National Wetlands Inventory, and that provides a hierarchical classification scheme based on the coordin way back in the day, but it still holds because it allows us to break the different types of wetlands up by system. So you see some examples here of an estuarine emergent wetland down in Masonboro Island versus a palustrine scrub, or what I'll be referring to as scrub wetlands for the talk, and then a palustrine forested wetland. So these are the main types of wetlands we kind of come across, along with riverine wetlands. And then that classification system goes down and down. The thing about the National Wetlands Inventory, we all love it, but it's severely outdated. It's very outdated for the majority of our state, and especially so for the coast, where we're seeing these very rapid population and land cover changes. So from a planning perspective, from the perspective that the folks were talking about just earlier, right? Thinking about green infrastructure, thinking about urban tree island, thinking about providing these ecosystem services and mitigating for floods and maintaining water quality and maintaining habitat, we don't really know what we're working with because the maps are highly outdated. Okay, so that's basically the takeaway from all of this. We have data sets, but they're fairly unchanged. And the way these data sets are usually created is from remote sensing, right? So we use a lot of remote sensing. We rely on a suite of remote sensing approaches that range from satellites that give us large coverage, aerial extent that is, and then we have airborne missions that kind of fill the gap in between, and nowadays we have more UAS types of collections that allow us to map these wetlands. So we can use remote sensing at from these different platforms to categorize pixels and group them into classes, just like what we saw earlier, right? What the Raleigh-Cary group is doing. And the goal is always to try to get more up-to-date and more accurate wetland maps. And again, there are two important data sets when thinking about mapping generally land cover, but specifically wetlands, right? The multispectral data that the NAPE, for example, the talk earlier was basically collects the way that different surfaces are reflecting back that incoming solar radiation, to be technical, but really it just we're mapping what things look like from the sky, from these different platforms in terms of just what is on the ground. So we can use that for vegetation classification. But the other really important data source that we can use to make much more accurate land cover maps are three-dimensional data sets, such as those given to us by LiDAR, light detection and ranging technology. And that essentially is what you're seeing there, kind of moving up and down from a platform. You're basically sending out an active laser beam, and you're collecting back the return. So you're collecting, depending on the technology and the specifications of the LiDAR, you're collecting one or two or multiple returns, and with those returns, we can create point clouds, and from those point clouds, we can make digital elevation, digital terrain models, which actually, and importantly, we can make something we call canopy height models. So we can actually measure how high, how tall my trees are, what is my stand inventory, what is on the ground in terms of buildings, and so on and so forth. And I'll come back to this in a bit, but in the state of North Carolina, we are actually very fortunate because we have one of the best statewide LiDAR data sets. We've had it for a while, but so we wanted to see essentially with this research, and I'll tell you in a second why, that we had one big objective, and that was, can we just use only LiDAR data and multispectral data, freely available, statewide, no fishy business, no fancy technology, nothing like that, to get accurate wetland maps. That's basically what we were going for. And then all the other stuff, wetland quantitative measures and predictor variables. But why do we want to do this? So what was the impetus for this? And the reason I had kind of Patrick working on this is because we had previously done a North Carolina Department of Transportation research project, NCDOT Research Project 2020-04, which was all about figuring out how the NCDOT can leverage UAS technology, and specifically LiDAR technology mounted on a UAS along with multispectral technology also mounted on a UAS to improve our current standard for wetland mapping at the NCDOT. And so for that project, we had surveyed all these 10 sites you can see on this map. I'm not going into details. This has been published. It's out there. I've talked about it in a previous setting. So we went across and did a range of a gradient of wetland sites from pilastrine to estuarine to everything in between. And again, the goal of this project was only UAS based. So the maximum that we could sample was anywhere between 80 to 200 acres on average. The average actually was 120. Anything beyond that was pushing it for the LiDAR. And we used essentially UAS mounted LiDAR technology. This is in 2020. Multispectral imagery, and then all the fancy RTK technology to essentially create these kind of cool, this is just to kind of give you a little, hey, this is how cool the stuff is. So this is one of our just point clouds coming from that LiDAR mounted on a UAS, which is now back with the NCDOT for their fabulous uses. And what we did with that project for these 10 sites, again, at very small spatial extents, we were able to classify out with really good accuracy, and I'm skipping over a lot of details, but we had training data from in the field, we had all the good stuff. We also referenced to NWI maps down here, NCDOT prior delineations, so we were able to essentially look at all these sites and create machine learning classifications and figure out that overall, we can do pretty well with UAS imagery, right? It's super high resolution. What we're looking at here is 10 to 15 centimeter accuracy, 4 to 5 centimeter vertical accuracy, really good stuff. Did okay, right? So, and then we figured out what was important in these classifications. We classified by category, pilastrine, scrub, pilastrine forested, and so on and so forth. And we did that. So that's my aside. That's why we did that, okay? So then my next thought was, okay, this is cool, but these are only 10 sites. They're really tiny. How much use is this really to anybody if it can be replicated? Because we can't fly UAS missions right across the whole state. So I wanted to essentially take those sites, the same exact sites now, except make them about 10 to 20 times larger, Okay, so the extent now, we're talking 2,500 acres per site around those sites that we had surveyed, that we had really good UAS data for, we had really good training data, we had ground control points, we had all checkpoints, we had all the good stuff. And essentially, so make the area bigger and only use freely available data. So that's what we did. So these are the study sites kind of listed on here. The name doesn't matter. What matters is that we were, again, trying to sample palustrine, estuarine, marine, and some riverine hidden in there. And we also had some of these study sites incorporated various types of other land covers, urban built environments, water bodies, other types of vegetative zones. And the only data that we used for this was the NOAA and USGS QL1 LiDAR data that was collected in 2020. And again, we did this before the data were publicly, they were still in beta version when we started doing this work. So we worked very closely with Mark at NCDOT, who was amazing, very supportive. So we got the data straight from them, did all the pre-processing to get that data to project the same coordinate system, get the vertical datums aligned and everything else. And then we used the 2020 NAPE imagery, so exactly the same year, everything else, with the 4 spectral bands. Again, this is multispectral data at that 0.5 meter, 0.6 spatial resolution. And then we just used, like I said, we used the NCDOT project. We call them wetland habitat points, but they were training data collected in the field that gave us information about what kind of land, what kind of wetland is there, what kind of species, and what else is kind of going on. And in addition to those data sets, because if you were paying attention, I said that we only sampled about 120 acres at each of these sites, so therefore we only had actual field training data for 120 acres kind of in each of these sites, but then we went with 2,500 acres. So we supplemented those training data from the field with on-screen collection. So we used ancillary data. We went to Google Earth, 2020 imagery, and so we created a lot more training data that way for our model. And we used a simple random forest algorithm. The other really cool piece, the other thing that I wanted with this project was to do it all in ArcGIS. And I decided to give this talk at this conference because the majority of the people here are not, I know this is not NCAUG, but this is like the smaller child of NCAUG, right? This is the less cool child of NCAUG? No, not funny? Okay, whatever. Don't tell NCDIT I said that. Hopefully nobody here from DAT? No? Okay. So where was I going with that? Yes, I was going with that to the fact that 2 freely available data sets, simple implementation in ArcGIS, okay? The previous project, we used R, we used all this stuff, parallel computing. I wanted to be able to do something that was simple, that could be replicated, where we could export a Python script, hand it over, you choose your area of interest, and you go with it. So something that didn't require scripting or anything else. So, to do that, we used the random forest algorithm that is actually in ArcGIS, and if you know about it, you know it kind of sucks. It's kind of like the grandmother of machine learning, is way back, but it works to some extent. So really, machine learning, random forest is just a simple machine learning algorithm that takes a big data set and splits it up into these multidimensional features, and then within those looks for ways that the data basically naturally breaks up into these kind of trees, and then you take them and from these from these bins, you essentially can create classes and turn them from data classes to information classes. And it's all random, and we can do other things with it. So a simple methodology. If you were to do this yourself, or if anybody wants to give us money to do it for the entire coast, we'd be happy to take it anytime. We would be able to bypass some of the Python PDAL work to get that USGS LiDAR data, to talk to the NOAA LiDAR data, because that's kind of been done now. But essentially, those data were converted to the correct height, and point clouds are made to give us, again, to give us some hydrologic variables and to also give us the canopy height models, which we wanted out of the LiDAR data. And then out of the multispectral imagery on the second column there, we were obviously after things like vegetation health, things like NDVI, the normalized difference vegetation index, but other indices that can be extracted, not too many from NAPE imagery. And then all of that sort of got put together, again, into the random forest algorithm in ArcGIS Pro, and we ran with it. Okay, so and we don't have to go over all of this, again, just from the NAPE imagery down at the bottom there. So for multispectral derivatives, we were only able to get NDVI and the normalized difference water index because of the 4 bands that exist with NAPE imagery. Other types of imagery, we could get more. And then from the LiDAR, all the other variables that you see over there, so the first, forget how many, 11 or 12, are all derived from LiDAR. And they all give us a little bit of information about hydrologic and hydric features that describe wetlands, such as topographic wetness indices, topographic position index, hydro condition DMs, digital elevation model, digital surface model, curvatures, all those things that allow us to kind of figure out how water's routing and tell us if it's a wetland potentially or not. And then notice the canopy height model, which is the other sort of derivative from that. And as I said, I'm not going to spend much time over this, just to say that this was all done using the forest-based classification and regression algorithm in ArcGIS Pro. Fairly straightforward. You just have to make some of these parameter changes. And then what you get out is an actual classification raster. You get your variable importance, your confusion matrix, and then some of the quantitative measures that will allow you to know how good your models are. So, some results in my last 5 minutes here. Now, I mean, the results aren't as cool. I think the approach is the cool part, because the results you can kind of do whatever with. So overall, the 7 sites that we looked at out of the 10 that we had done for the DOT show that for the average overall accuracy was greater than 80%. That's pretty good to get, again, with only 2 data sources really available, and an ancient kind of algorithm as it is, random forest is implemented in ArcGIS Pro. And then we got sensitivity and specificity metrics, which tell us the false positives and the true negatives for these models. And on average, you know, we can talk about that. They range, and I'll show you a little bit why and how they range. And here are some of how these data look like. So again, you could, just like the speakers before me showed, we can go into this and break it up into a variety of different classes. But for the purposes of this project, we were just looking at non-wetlands, so everything that isn't a wetland is in gray, and then we were after specific, all these wetland classes, right? So all of those are symbolized with respective colors. Again, it was a little bit difficult to differentiate between non-wetland vegetated zones and wetland vegetated zones for obvious reasons, right? Because we only have these 2 data sets. There is a stark contrast between these vegetated and non-vegetated wetlands. And then overall, for the variables that are really important, because this is good to know, right? If you were to do this again, should you calculate the topographic wetness index? Should you calculate the curvature? Well, I can tell you probably not. So these variable importance plots allow us to figure out what of all those initial variables we threw at the model are important. And I would say these NDVI, so the normalized difference vegetation, so your vegetation health metric, your canopy height model, DSM, and a couple other variables that we derived from the LiDAR are important, but some of the other ones we had calculated were not so important. And the canopy height is especially important, as we would imagine, and we will see in a second, for differentiating between your tree wetlands, your forested wetlands, and your scrub wetlands versus your estuarine wetlands. And again, this is why we want to leverage LiDAR data to look at these kind of canopies, right? Your multiple canopies. What is a marsh versus what is a forested or a scrub wetland? And I can't stress enough just how important the LiDAR metrics are to do that. So then We looked at them by essentially by class. So on here, you see all the sites that contain more than 40 or 50% palustrine forested wetlands, right? We symbolize them like that. And you can kind of get an idea of what the top variables, like I said, are canopy height and NDVI, right? And the overall metrics, again, they range from about 60, overall accuracy was above 80%. But then if you look at the sensitivity and the specificity, that's where we kind of get into the details and have some variability. Now, if you look at scrub wetlands, these ones, the palustrine scrub, these were the most difficult to classify overall. And it makes sense because they are the pocosins, they're very dense, they're very mixed, and I would say that you can see that we were down to in the 40s for the sensitivity for some of those sites, and especially the sites. So, but again, canopy height derived from LiDAR and DSM are really our top most important variables. And then if we go to emergent classes, right, essentially your marshes in the coastal zones, these ones perform the best. Obviously, it's a little bit easier to map these out. Overall, and here the digital surface model was the most important variable. So the canopy height model, by canopy height model, I just mean the difference between the DSM and the DTM, right? So, or the DSM and the DEM, but that's less so important in a site like that. And lastly, the other thing that we were looking at is kind of how this kind of a classification compares to NWI data. So we can do this quantitatively. And kind of get an idea. So in the bluish is the NWI extent, and then our predicted emergent, which actually fills in some of the details and is able to be a little more discretionary with the overall aerial coverage than what we can get from NWI. Anyways, I can kind of go into details, but I think I'm out of time-ish. Okay, so I will leave it as this is a cool. Gary took this photo. We lost a drone to one time, a long time ago. We lost a drone to this estuarine wetland here. We found it again the next day, and so we got a gator in the picture. But the bottom line with this is that we can get over 80% accuracy overall, right? Sensitivity and specificity, when you get down to those at the class level and site level, there are some important differentiations. But we can definitely tell the difference between forested scrub and estuarine wetlands pretty well. And the real bottom line is that we do need additional training data. So we need to be getting out there in the field. We also want to put in more distance-based predictors, streamlines, floodplains, hurricane flood zones, all the good stuff. But overall, we think that this could be a promising method for creating a more updated wetland inventory data set for the state using these simple data sets. And I think they would perform a lot better if we used, a better, more robust classification algorithm. But anyways, that's it. And I want to thank Mark Schwartz at DOT, my colleague Joanne Halls and Tracy Chan, and all the students that are listed on that third line who helped with the original data collection for the UAS, the NCDOT project, and everybody else. Thank you. Oh, and I want to put a plug for UNCW's new Coastal UAS Observatory. If you hadn't heard about it, we are accumulating all this amazing instrumentation with a grant from the National Science Foundation, and we can do a lot more and cooler stuff. Get in touch with me. And I have 8 minutes for questions. Yes, please. Yes, we have. We've tried. Well, we have the data, but for just presentation purposes, I wanted to kind of keep it at the system level. But yeah, we can. We have it. Okay.
So a lot of your most important variables came out as kind of general vegetation differentiating vegetation from non-vegetation.
Sure.
You have a hard time differentiating wetlands and mountains.
Yes. That.
What else you could include, whether it is LiDAR derived or are there intensity metrics you could use on something last return that would maybe be helpful?
Yeah, no, for sure. And I think that's what I was saying, that we really need additional variables. This was kind of like a first, we were actually doing this to kind of match how the DOT does their wetland prediction model. So we were kind of using exactly those same variables, except derived from the QL1 LiDAR. But yeah, so we can put building footprint, so we can try to help. We need to do better discerning between those. And that's a good idea with the intensity returns. I hadn't thought about it, but we can definitely bring in building footprints and all that kind of stuff to kind of try to account for. I was intrigued by your impervious below canopy. That's a cool metric. If we can figure out that, then that would help us a lot to differentiate those two classes. Yeah, that's a good idea. Yeah, we have to. Yeah. Yes? They had what? Yes, PDAL. Uh-huh. We say PDAL. I don't know. You say. Yeah, but like I said, we got the data in beta version, and it hadn't been, yeah. Oh, in QGIS. Okay. PDAL, okay. Sure. Absolutely. But again, I was trying to kind of come up with something that we could essentially hand kind of a clean automated model to a municipality or to a county like that. Yeah, but that's definitely within. Yes, plug in QGIS. That's a good idea. Yeah. Any other questions, please? Yes. Yeah, I mean, I think it would all come down to how we train and how we segment our imagery, right? So kind of back to that, we can totally do an image object-based analysis. You did better with object? Yeah, I mean, yeah. We've done, for that DOT project, we did actually both object and pixel-based. We actually went with the pixel-based because it did do better. Pixel-based did better with the drone, so I stuck with pixel-based for this. But yeah, I think from imagery, from non-UAS imagery, object does do better. Yeah. Yes? We are trying to get a publication out, and after that, yes. Yeah. Any other thoughts, questions? Yes. Yeah, definitely. That was one of the variables that we should definitely include. Yeah. I mean, that's the thing. You can always throw in more variables, but I really just wanted to see how well can we do with just these two things. Because then, all the other stuff, we do throw soils and impervious and all the other good stuff. Oh, definitely. Yes, yeah. But in the coastal zone, some of these more topographic-based variables do give us a good indication in general, because most everything is a wetland. Well, we used to be. All right, thank you very much, everybody. If you have any other questions, send me an email.